So in this module, we are going to talk about 1,3 and 1,4 dimethyl cyclohexanes. In the previous module, we have already spoken about 1,1 and 1,2 dimethyl cyclohexane. Now both these molecules, that is 1,3 and 1,4 dimethyl cyclohexane, exist in two geometrical isomeric forms, and we call them as a cis and trans. So if I take 1,3-dimethyl cyclohexane, cis means either 2-methyl or beta or 2 methyls are alpha, and this is how we'll represent in planar form. Whereas in trans, one will be alpha and other will be beta. So this is how we represent the trans 1,3-dimethyl cyclohexane. The relation between two methyl groups for cis 1,3-dimethyl is either equatorial or axial. Whereas for trans, it is either axial equatorial or equatorial axial. Similarly, the cis 1,4-dimethyl cyclohexane, where both the methyls are either beta or alpha, the relation comes to be axial equatorial or equatorial axial. Whereas trans 1,4-dimethyl cyclohexane shows the relation as equatorial or axial. So let us see now the more details about these molecules and talk about the energy calculations and stability. So cis 1,3-dimethyl cyclohexane, see I have shown here both beta, and if I'm supposed to represent in chair form, then if this is my first carbon, the beta will be axial, and third carbon, which is alternate with respect to first carbon, next methyl will also come as a beta axial. So the relation between these two methyls, which are cis with respect to each other and at 1,3 position, comes to be axial. If I flip this particular chair, then I'll find that the first carbon methyl is still beta, but it has become equatorial, and third number carbon methyl is still beta, but is again equatorial. So as we know that after flipping, axial becomes equatorial. So the relation after flipping now is equatorial. So these two chair forms both represent cis 1,3 dimethyl cyclohexane. Now, you can see here that since the number of axial bonds are not same, there are two axial methyl in the first form, whereas in second form, we do not have any axial methyl, means their energy will not be same. So let us talk about their energy calculations. It is observed that the cis diaxial 1,3-dimethyl cyclohexane has energy around 5.4 to 5.6 kilocalorie per mole, and if I compare it with the equatorial form, its energy is minimum and it is taken as 0 kilocalorie per mole. So out of these two forms, one can easily say that the one which has a lesser energy will be, obviously the equilibrium will be more towards this particular form of the cis 1,3-dimethyl cyclohexane, as it is highly stable, and therefore we show the arrowhead more towards the di-equatorial form as compared to diaxial form. Let us see the energy calculations. Now, as I know the thumb rule that if there is one axial methyl, then it has two butane gauge interactions with the ring bonds, and since there are two axial methyl groups in the diaxial form, therefore there will be four butane gauge interactions. If four butane gauge interactions, then I expect that the energy should be 3.6 kilocalorie per mole, as one butane gauge interaction increases energy by 0.9 kilocalorie per mole. But it was observed that the energy is still higher than 3.6 kilocalorie per mole, and it is approximately 5.4 kilocalorie per mole. That means there is a difference of 1.8 kilocalorie per mole. Now, what is the reason which makes this molecule more energetic or more unstable? So, it was observed that there is one more interaction introduced in this molecule where two methyl groups or two bulky groups are in the same plane, and that interaction is called as 1,3 diaxial interaction, which increases energy by 1.8 kilocalorie per mole, and therefore total energy is 3.6 plus 1.8, that is 5.4 kilocalorie per mole. More details about 1,3 diaxial interactions we'll see later on. But this is how we do the energy calculations for diaxial form. And if I take di-equatorial form, you can see that they are very much apart from each other. They are away from each other. There is no butane-Gauge interaction between these two methyl as well as the ring bonds, and therefore energy of di-equatorial form is taken as 0 kilocalorie per mole. So this is how we calculate the energy and talk about the stability. Now let us talk about the optical activity. See, you can nicely see that there is a nice axis of symmetry for both diaxial form as well as di-equatorial form. So this particular molecule has a axis of symmetry, or here I have represented a plane of symmetry. So both indicate that this particular molecule, even though has chiral centers, both first and third carbon, they're chiral, but they have a plane of symmetry and therefore are optically inactive. So this molecule is a mesoform, and due to internal compensation, this molecule becomes optically inactive. So both cis diaxial as well as diequatorial forms are highly unstable. Now we have come across a new thing, that is 1,3 diaxial interaction. Now what is this 1,3 diaxial interaction? So you can see that if these green balls indicate methyl groups and they are 1,3 in a diaxial form, both are going in upward direction, both are beta, they are coming in the same plane, and therefore they start repelling each other. If I flip this particular chair, you can see that now it becomes a di-equatorial form, and there is, you can see that they are very much apart from each other. Still both are beta, but they are not in the same plane, and because of that, in di-equatorial form of cis 1,3 dimethyl cyclohexane, these two methyl do not have any interaction or repulsive forces. Whether I see from top view or from the bottom side, I'll find that both with beta or alpha methyl diequatorial form, uh, both will have energy 0 kilocalorie per mole. But the moment I flip it and convert it into a diaxial form, now here both methyls are alpha, and what you'll find, whether it is alpha or beta, these two methyl groups are coming in the same plane. They are very close to each other in space. They start repelling each other, and this interaction, this repulsion, is called as 1,3 diaxial interaction or repulsion, which increases energy by 1.8 kilocalorie per mole. So what is 1,3 diaxial interaction? So you'll find that in 1,3 diaxial interaction, two methyl groups are in the same plane, which are located at the alternate carbon atoms, and these methyl groups, since methyl is bulky, you'll find that the space between two groups will be very less, and because of that, this particular molecule becomes highly unstable. So if I am supposed to show this 1,3 diaxial interaction, diaxial indicates that both are axial, and since they are coming in the same plane, this particular molecule has a uh, interactions between these two methyl and makes this molecule highly unstable. So this is called 1,3 diaxial interaction. The distance between these two groups is less than van der Waals radii, and as we know that if the distance is less, then they will start repelling each other, and that will increase the energy by 1.8 kilocalorie per mole. This is called 1,3 diaxial interaction, as they are in the same plane, they are close to each other and start interacting each other. So that is why energy of cis diaxial 1,3 dimethyl cyclohexane is more than expected, and it is about 5.4 kilocalorie per mole. Let us go for the another molecule, that is trans 1,3-dimethyl cyclohexane. In trans 1,3-dimethyl cyclohexane, you'll find that trans means one is beta, other is alpha. If I see the write the first carbon atom methyl as alpha, then third number carbon methyl will be beta. And if I flip this particular molecule, then the after flipping, the first carbon methyl becomes axial, whereas third number carbon methyl becomes equatorial. So the relation is equatorial axial or axial equatorial. Now, let us talk about their energy calculations. In both the molecules, they have same number of axial bonds. That is, one axial methyl is there. And therefore, there will be two butane-Gauch interactions, and hence the energy is 1.8 kilocalorie per mole. So, this is how we can show the representation for trans 1,3-dimethyl cyclohexane, and you'll find that since both have same uh, butane-Gauch interactions, the energy of these two molecules is same. If I compare this transform, this is a cis equatorial, this is a cis diaxial, and this is my transform. You'll find that the energy of diaxial is highest among all one disubstituted cyclohexanes, and the diquetral form is the most stable, whereas the trans 1,3-dimethyl cyclohexane lies in between the trans diaxial and trans diequatorial form. So this is how we do the energy calculations. Now this particular molecule, like your cis 1,3-dimethyl cyclohexane, does not have plane of symmetry. You can see one is beta, other is alpha, and therefore it is a optically active molecule. It is resolvable DL pair, as there is no symmetry and it has chirality, it has two chiral centers. Therefore trans 1,3-dimethyl cyclohexane is optically active molecule. The second molecule we are going to talk about is 1,4-dimethyl cyclohexane. Now 1,4, they are opposite to each other, and again it exists in two forms, that is cis and trans. This is the planar cis 1,4-dimethyl cyclohexane, where two methyls are beta or two methyls are alpha. If I show in the chair form, this is how the chair will look like. If this is alpha, the relation comes as equatorial axial, and after flipping, it becomes axial equatorial. The alpha remains alpha and beta remains beta. That is what you will see. So cis 1,4-dimethyl cyclohexane has a relation either axial equatorial or equatorial axial. Now both the molecules have same number of axial bonds, and therefore their butane-Gauch interactions are also same, and hence they are equally stable and they have energy 2 into 0.9, that is 1.8 kilocalorie per mole. Now this is your trans 1,4-dimethyl cyclohexane. Trans means one is beta and other is alpha. If I represent in this form, then I'll find that either the relation comes as a diequatorial or it will come as a diaxial. So this is your diequatorial trans 1,4-dimethyl cyclohexane, whereas this is diaxial 1,4-dimethyl cyclohexane. Now, since they don't have same number of axial methyls, their energy will not be same and they will have difference in their stability order. The diequatorial form does not have any butane-Gauch interaction, and therefore it is highly stable and its energy is taken as 0 kilocalorie per mole. But a diaxial form, since there are two axial methyls, there are total 4 butane-Gauch interactions, and therefore the energy will be 4 into 0.9, that is 3.6 kilocalorie per mole. So obviously the diaxial form is much highly energetic as compared to diequatorial form, and since its energy is high, its stability is less as compared to diequatorial form. Now let us talk about the optical activity of all 1,4-disubstituted cyclohexane molecules. First, I have represented a trans and this is your cis. And what you will find that whether you take cis or trans, all these molecules, they have axis of symmetry passing from first to fourth carbon, and that is why all 1,4-disubstituted cyclohexane molecules are optically inactive because of axis of symmetry or plane of symmetry. So, whether you go for a cis or trans molecule, whether both the substituents are same or two substituents are different, doesn't matter because of this plane of symmetry or axis symmetry. And what you'll find that all 1,4-dimethyl cyclohexanes are optically inactive. So this is a plane of symmetry among these molecules, whether you go for cis or trans, and therefore these molecules all are optically inactive. So remember, 1,4-dimethyl cyclohexane is always optically inactive. One more thing we are supposed to consider, learn, that is locking of conformation. Now what you will find that whenever substituents are one-fold to each other, and if you have a very bulky substituent at one of the carbon, let's say a bulky substituent like tertiary butyl group or isobutyl group, what you will find that this is, let's say, one form, and if I imagine the flip form, then this is how I will draw the flip form of this particular chair. Now what has happened here, the bulky group which was equatorial has become axial after flipping. And as we know that whenever you have any axial bond, it makes the molecule highly unstable because of butane-Dutch interactions. And it is observed that whenever bulky group like tertiary butyl group is axial position, at that time the molecule becomes highly unstable and therefore the flipping of the molecule is hindered. It does not undergo flipping and it remains in only one form where the bulky group is equatorial, and no flipping of such kind of chair will be observed, or you'll find that 99% of this particular molecule will exist in the form where the bulky group acquires equatorial position. Now, a small group like methyl, it can be equatorial or it can be axial. That does not decide the stability, but the stability of the molecule is decided by this bulky group orientation, and it is observed that such kind of cyclohexane molecule, even though it has now all CC bond, single bonds, CC bond rotation is possible, but it does not happen, and molecule gets locked in only one conformer where the bulky group is at equatorial position, and this is called as locking of conformation. See here now that you have a methyl which is axial and you have a tertiary butyl group which is equatorial. If I flip this, it acquires the axial position and this is equatorial. Now this is your 1,3-dimethyl cyclo, 1,3 substituted cyclohexane molecule. What you'll find, no flipping will take place for this molecule. It will exist in this form only and not in this form. This phenomenon is called as locking of conformation. So this is how we calculate the energy and study these dye-substituted cyclohexane molecules. So thank you for watching this video and kindly subscribe the channel. Thank you.